Enough, you guys. Reaction rates, we're dealing with a lot of math. Ultimately, this section is probably one of the sections in this class where we do the most math-related material, where 90% of the questions that are asked are solvable questions where you actually get some number, okay? In reaction rate stuff, and any problem relating to reaction rates, we're primarily focusing on the reactants, okay? In Chem 105, we looked at reactions as a whole, we balanced those equations, and we did a lot of stoichiometry, where with the coefficients in front of each reactant and product, we were able to predict how much product might form in a certain situation. Now, with reaction rates, we only care about the reactants. Everything we're doing is studying what the reactants are doing and how quickly that reaction is happening. So in order for us to solve any problems with this, we have to have some data. Reaction rate problems are going to give us a lot of data. And basically everything in reaction rates goes through the same type of solution. When I say that, what I mean is everything we're solving for in any chemical reaction dealing with the reactants, we're looking for some type of rate law. Because that is like our master equation that we could write for any chemical reaction and ultimately tell us a lot of things about that reaction, okay? So to begin, the most basic type of data that you can be given is something like the luminol problem in your recitation quiz, where you're given a graph that has time as the reaction proceeds and one of the reactants, concentration, or it could be the only reactant in this case, right? And how that concentration is changing over time, okay? So in a graph like this, there's a lot of things that we can start to understand. First of all, how steep this slope becomes as the time of our reaction takes place, it directly reflects how quickly the rate of that reaction is happening. So for instance, up here where the slope is pretty steep, the reaction is happening quicker than it is down here. And if we try to conceptualize something like that, let's think about some of these lists that you're supposed to know for the test, like the 4 things that affect reaction rates, right? We have temperature. As temperature increases, we can increase our reaction rate. We have the physical state that those reactants happen to be in can increase the reactant rate, because ultimately, like the collision theory tells us, and we're going to get into that later, to have a reaction take place, I have to have one reactant come in contact with the other, right? And so depending on what physical state these two reactants are in, they might have a better opportunity to collide with the right energy and in the right orientation, right? And also concentration or having a catalyst will speed up a reaction. So as we look at this, right, as time proceeds, we're obviously losing the concentration of our reactant. So it makes sense that this line should mellow off and our reaction should slow down, because concentration is one of the things that affects these rates, right? So as we're losing our reactant here, there's not as many molecules to react anymore, so it's starting to slow down, okay? So a couple of the questions he can ask are things like this. He can ask you an instantaneous rate at a very particular point of this reaction, or the average rate for a given amount of time. So what that looks like is, what would be the instantaneous rate at 50 seconds or 50 hours, depending on what my units are here, right? I go to my graph, pick 50, come up to my line, and I put my point up, right? If I want an instantaneous rate at that point, I want to just solve for what the slope is right there, right? So I do what's called a tangent line, and I'm not good at drawing these, but you'll have like a straight edge on your exam, right? So I want to figure out what's the slope at that point. If I solve for the slope there, that tells me what the rate was at that position. Now this is different than from saying, what is the average rate of change or disappearance or appearance, right? From 0, from when it began, from when the reaction began, to maybe like 100 seconds. In that case, we're going to start at 0 and come over here. So we take where the reaction was at 0, and then we draw a dot where it was at 100, and we just connect those two, right, in a straight line and solve for the slope of that line. That would be the average rate of reaction from 0 to 100 seconds, okay? So those are the two types. And as we look at this, it's important to understand the difference between a rate of appearance, a rate of disappearance, or a rate of change, right? With appearance and disappearance, it's easy to understand that, okay, if I have a reactant and it's trying to form a product, I'm obviously losing that reactant as it forms product. So it will be disappearing as a product appears. So when I say something like this reaction disappears at 5 molarity a second, I don't have to give you a negative sign or a positive sign because I'm telling you the direction, right? But if I just said such and such compound rate of change is positive 5 molarity per second, it sounds like it's gaining 5 molar per second of that compound. But if it was a reactant, what I meant to say is that I'm losing it. So anytime I deal with a problem that asks me for a rate of change, those values, it's particular to whether it is a reactant or a product. Therefore, if it's a reactant, rate of change is a negative number. I'm losing reactant as I go. If it's a product, I'm gaining it, okay? So just keep that in mind as you solve those types of problems and look for errors with that. So as we continue with reaction rates, we're always given an equation, right? And it's up to us to analyze the equation, and usually the first type of problem they give us deals with a set of experiments that they've done, and they've calculated how quick the rate occurred, what concentration did they use for each reactant, and ask us to solve for a complete rate law. That is the number one type of problem that is almost guaranteed to be on your exam, okay? So one thing that's important to note is when I have a normal chemical equation, my coefficients in my balanced equation don't tell me anything about the order of that particular reactant, right? Just because NO here has a coefficient of 2 in its balanced equation does not mean that it's second order, particularly for this reaction. Now, it might come out to be, but that's not what's telling us it is, so keep that in mind. But it's important to note that that is only for normal balanced chemical equations. When we get into elementary steps, the coefficients do matter. So make sure you separate that in your notes and in your mind, that we're not looking at the coefficients here. You guys have done a lot of problems like this, so we're going to speed through this a little bit. But I want to make sure this is ingrained in your minds. This is the way you solve these problems. There's not another way or something different. Now, you might do your math different, which is totally cool. But ultimately, these are the steps you'd want to take. In order to write a rate law, all of you know what a rate law looks like, right? I have my rate is equal to my K constant times the concentration of one of my reactants times maybe the other one, right? Raised to their powers. So as I look at this, I have what my rate happened, right, for a particular experiment 1. I have what my concentrations were. In order to figure out what these values are, which is ultimately the hardest thing to solve for, what is the exponent of each reactant? How does NO change the rate? Is it exponentially different, or is it just an exponent of 1? So whatever I do to this one, it does the same thing to the rate, and things like that, right? So I want to pinpoint one of them and decide to solve for. So if I want to figure out what the exponent of Br2 is, I look at my experiment and I pick one where NO remains the same throughout it, right? And I'm changing Br2. And I do that because if I keep NO the same, then I'm basically controlling for that reactant and looking at how the other reactant is affecting the rate, right? So the perfect experiments to try for Br2 is experiment 1 and 2, because NO I keep the same, but I'm doubling Br2. So when I do that, I look over and see how the rate changed. And the rate from experiment 1 to experiment 2 also doubled. So if I doubled Br2, I didn't do anything to NO, my rate also doubled. What exponent is that? An exponent of 1, right? If the same factor of change is happening to the rate that's happening to my reactant, then it's just 1. So I immediately know, just by eyeing it with no math, that the exponent for this one is 1, okay? That is usually how this goes. You can eye these problems and look at how they would change. Now, the next one we could also eye, but I want to go through how would you solve it if you weren't sure. By just looking at it, you didn't want to fumble that math. So how could you go through something like that? Well, if we already know Br2, let's look at what experiments we would want to use for NO. Maybe 2 and 3, because Br2 remains the same. And with 2 and 3, we double NO. So to do this, what we want to do is ultimately set the rate of experiment 2 over the rate of experiment 3, right? And so the rate laws for each one, so I got my K here for both, over the concentrations of NO raised to their power, which I don't know, and my Br2. Okay? And I know that that one is 1. So I plug in the data that I was given. I plug in my 2 rates. So my rate 2, rate right here, is going to be 0.08. And here is 0.32. Okay? My k's, I don't need to know that number because they're the same. How do I know that my k is the same? Because I'm assuming this was done at the same temperature. If it wasn't done at the same temperature, are they the same? No, exactly. So my k is the same, so they cancel. So I'm not going to worry about them and just erase them, actually. Also, for experiment 2 and 3, my value inside of these brackets for BR2, I kept the same for reason, so I could just erase the whole thing. So I'm left with whatever my concentration of NO was for experiment 2, which is 0.1 over 0.2. So both of these are raised to the n. So this next part is just an algebra thing where we're just going to simplify to solve for n. So in order to simplify this, I just literally do this division now. Okay, I do this division, and then I do this division, and I simplify. Let me see, I think I should be 0.25 is equal to 0.5 raised to the n. So when I divide these two, this exponent here, I'm not canceling those, but rather it just remains with what this number now is, okay? And then here, once we get to this point, it's just something you have to memorize how to finish this. It's just a log rule, right? These are all log base 10. And so in order to solve for this exponent, I say the log of my left side, 0.25, over the log of my right side, which is 0.5, is equal to what that exponent is, okay? Just memorize that. Again, the log of your left side divided by the log of what this number is will equal what n is. And when you do that, you get 2, right? So then it's a perfect 2. So we know that n is 2. So NO here is squared. And this one is raised to the first power. Are there any questions with that? You guys have done problems like this. This is just sort of to just solidify in your minds, you can do that process with any of them, okay? All right. So now that I know what the rate law mostly is, I have my rate is equal to K times NO squared. Okay. So now that I know my rate law, do I have a complete rate law for Dr. Macedoni's class? What am I missing? Exactly, I'm missing my k. So, to solve for the k, I can plug in any experiment and what their concentrations were and what their rate were. So the rate here and their concentrations, I now know their exponents and solve for k. It is probably of your best interest to do it for all three, and the k's will just maybe be different by a little bit and average them. So you get the best k, okay? So as we look at this rate, remember, it's up to you to solve for the k. Okay, don't forget to do that. Make sure you put a real number in here. And also, if that number is going to be valid, what do you have to tack on to the end of it? The what? The units. You have to write their correct units. There might be answers on your test which all differ just by their unit, but it's the same magnitude. So you get your k and you're like, oh my gosh, all of the answers are that number that I got. But the units change. So looking at this, knowing that, what are the units for rate always? It will always be in molarity per second. It will never change from that, right? So we have molarity per second is what our unit is on the left here. And so far, what are the units that I have in the numerator of this side, right? I have, this is molarity and this is molarity. So I have molarity squared times just molarity, which gives me molarity cubed, right? What do the units of my k have to be over here so that it cancels to get this? Well, I know I need seconds in the bottom, so it's going to be a second in the bottom for k. And also a molarity squared, so that it cancels with 2 of the 3 and leaves me just one other. And so how could I write in the form of k what molarity squared times second in a denominator looks like? It's just molarity minus 2 seconds inverse seconds like that. Okay, so that's the unit of your k. We're going to look at a problem in about 10 minutes. How important is it to get the correct units? And if you were given the units of a k, you can ultimately predict almost everything about the order of your reaction, right? So what is the order in this rate law? What is the order for NO? Second order, right? Because if I want to know an order for a particular reactant, I look for just that reactant and what its exponent is. But what is the order for the whole equation? It's third order, okay? So make sure you differentiate between those two orders. So I'm going to keep that rate law up there. As we look at this, now, these over here are the elementary steps that actually occur to have this reaction happen, right? So what if you were given a question that said, what is the slow step? So ultimately, you know what the rate law is, right? So you're not doing the problem where you're solving for the rate law, knowing the slow step, but you have the rate law and are predicting the slow step. So when we do a problem like that, remember, in a reaction, in these elementary steps, ultimately the slow step is who determines how quick you are. It can't get over that. It doesn't matter how fast the fast steps are, the entire reaction is dependent on how slow the slow step is, right? Elementary reactions differ from normal reactions because elementary reactions are the things that are elementary. They are the beginning basic steps. It is exactly what happens in real life, meaning NO gets together with NO to form that, which then goes through this process to get me here, right? Versus how it's written up here, right? There are some pieces in this that aren't shown, but in real life, they were there and did occur, okay? So elementary steps are important, and how they differ with reaction rates is that with elementary steps, whatever my coefficients are, that is the order for that specific reactant, right? So over here, that's not the case, but for elementary steps, it is. So if I want to predict what is the slow step, and I have the rate law, I want to look at if I made either one of these the slow step and then wrote a rate law, does it match up with the one I got over here? Because it has to, right? So let's try this. If I say, okay, let's say the first step is the slow step, meaning I have to write my rate law according to the first step. So in order to do that, I know that my rate in the forward direction is ultimately how I'm going to look at this equation to write the rate law. So the rate law for my forward step would be my rate is equal to K times the concentration of NO times another concentration of NO. And each one is raised to the first. So how could that simplify out? It's just NO times NO. So we could just say it's NO squared, right? So I could just say that's really this for the rate for the top step. So does this rate law match up with this one? No. So I know that the first step isn't the slow step. So obviously in this case the second one is, but let's look at why. How could you prove it? So if this was the slow step and this is my fast step, I have to write my rate law according to this step. So I was going to try to do the same thing. I'm going to write the rate and say that my rate is equal to the concentration of this raised to the first power and the concentration of that raised to the first power times the K. Well, what is the problem? Why is it not that simple for this one? Because this compound right here is an intermediate. And again, in reaction rates, we're trying to measure these values to predict how quickly a reaction occurs. So it's impossible for us as scientists to have something be happening or being produced in a top equation and then try to hurry and measure it before it starts to react. These reactions are occurring so fast that there's no way you could freeze time to record how much was there and then predict how much is going to be for a rate law. So ultimately what we have to say is, well, because I can't use this, because it's being formed and then used, so it's an intermediate, I have to put something in its place that I know is equivalent to what that value would be equal to. So in order to do that, I got to go back up to this top step, and I say, okay, now I get into a little bit more trouble. I have to try to say that the rate of this direction for the top is equal to the rate as if it was going backward. So almost as if I just flipped this whole equation and looked at it the other way. And I know that is true because of these arrows, right? These are equilibrium arrows. And when anything hits equilibrium, it's when the rate of the forward reaction equals the rate of the reverse reaction. So what I got to do here is say, okay, the rate of this side, which was NO, those are ugly, times a K1 is equal to a K reciprocal 1 times this. Okay, they're all raised to the first power. So in order to get what this might be equal to, I'm just going to divide by that piece, and that's all I'm going to do. So I'm going to get that my concentration of N2O2 is equal to K1 divided by K reciprocal 1 times NO times NO. Right? And that's what it's equal to. So then, instead of plugging my rate law, instead of plugging this value in for here, I'm going to plug in what it's equal to. So when I'm going to write a rate for my second step, I'm going to have my rate is equal to K2 times K1 divided by K reciprocal 1, some mess of K's, times NO squared, because that's what this equals, NO times NO, times, okay, and that does match the rate law that I got. So that's how I know that my second step there is my slow step. That's correct, okay? So when you do this in the end, you don't necessarily have to write your K's all messy like this. You could just maybe write this off to the side, and then maybe when you do write this out, write K new, right? The new K, which you know is equal to this off to the side, okay? All right, so we have about 5 minutes to go through the last type of problem, because that covers almost just doing that problem alone, and if you can master that type of problem, you have basically covered almost all of the letters in your necessary skills list, just understanding how to do a problem like that, right? That's basically most of it. So the next type of data you can be given is a graph that gives you time and a concentration and how it's changed. So it's basically just a chart of what this graph is. So, and you guys remember, in order to figure out the order of your reaction, which was something we're always trying to do, there's a method that we can do. We can graph the data, where we take our values of our concentration of A, and we take the natural log of all those values, or 1 over that value, and put our numbers in our chart. I always like to extend my chart and make it like this. And then, if I just graph this data using time always as my x-axis, and either these as my y, or this is my y, I look for the one that gives me what type of line, you guys? Straight line. And the graph that gives me a straight line is that particular order. Okay, so I suck at freehanding graphs. It's like the hardest thing to do. Every time I would freehand a graph, I would get 2 lines that look straight or both that look curved. So what I like to do, and what Corbin also likes to do this, is instead of graphing it out, I like to just solve for what the slope is between 2 lines. So if this was a line here and this was the line here, right? If I already knew what the graphs were, the slope between a point here and a point here will equal the slope between this point and this point, right? They'll be the same. But the slope between a point here and a point here will be steep, and a slope between the point here and a point here will be mellow out, so the slopes will be different. So if I just do rise over run for a series of data using these as my values, and I keep getting the same slope as I go through it, that's the straight line instead of having to freehand it or put it in my calculator. So if I do something like, so rise over run, I'm going to take y2 minus y1 minus x2 minus x1. So I'm going to get 146, oh I did it right, 146 minus 100 divided by 60 gives me 0.77, I think it's 7666, and it keeps going, right? So then I did it for those 2 data points, now I'll do it for these 2. And I take 239 and subtract, I take 85 and subtract 239, and then I take 240 minus 180, which is 60, and I again get 0.7666. So I notice that the slope between these 2 pieces and these 2 pieces are the same, or a situation like this. And I know that I use this data, so this is my straight line, right? So what, if this is, and this is the case for this data, what is the order of this reaction? Second order, right? And you need to have something like that memorized. Do you have a question? Okay. So an important thing, I know we're rushing through some of this, but if you can do just this problem, all of the problems are like this. This is how they work. Now, when you get your straight line, there is more information still with the line that you get. So if you know your slope in a graph that has these as your x and y coordinates is equal to your k constant, right? Always. So that was what happened on the luminol problem on your recitation quiz. You guys need to memorize that. Have that down. When you get your graph for which one creates a straight line, take the slope of that line is equal to your k constant. So ultimately, you can write rate laws, or you could use even this right here. If you didn't find the slope or didn't want to look at your slope, you can use this equation to also solve for what your K is or what your concentration of your reactant was at some different time that might not be listed there, right? Or something like that. So when you do these problems, you guys, it's imperative that you have memorized which equations go with which order. Because you have your toolbox, and you're going to be given your equation sheet, but it's still up to you to know which equations go to what, because you're not going to have the toolbox laid out and the equations in the order that you've been seeing them. So if you can go out and write all of those equations like freehand and know which ones they go for, or which order they pertain to, that is when you know that you're prepared, okay? So any questions with figuring out the graph? I like the slope to just solve for the slope because it works way easier. And a little note about that, let's say you take 2 points and get a slope of like 7.8. And then you get you take the slope of other 2 points, and you get something like 7.6 or 7.5. Both of those just round to 8. And so that's still your straight line. So what I've noticed is the points don't always come out to be perfect, but they always will round to the same number, right? Always. And so I would double check and maybe do a bunch of points, but it always has to round out to that.
So if it's the first column and it's 0th order, you know when you just have the concentration, you have that?
Yeah, it's just equal to K.
Okay.
Yeah. Okay, so the last thing I want to look at in our last 2 minutes is this problem. If you had a unimolecular reaction with this K, could you write a complete rate law? Why? It's whatever it is, unimolecular, or I guess, I think this works, but I don't want to, it might get a little bit confusing, so stick with me on this, okay? Unimolecular, you guys know what that means, right? It means that all I have is one reactant that's decomposing, or it's the only thing that is in this type of state, right? If I get bimolecular, it means that ultimately I have 2 reactants that are coming together to react, okay? But my point here wasn't really supposed to be about the unimolecular. I just wanted to use a term so that you guys remember you need to know the molecularity. But what I wanted to highlight again is if you're given a K, if you have the units of the K, and what I meant by unimolecular was that there was only one reactant, right? Ultimately just one reactant. But if you know the units of your K, you know the order of any reaction that has one reactant, right? So it might not be correct in this real situation to put unimolecular for something that with these units really comes out to be second order, right? But I want you to remember that it is the units that are the most important thing, okay? The units of your K can tell you basically everything about your reaction, all right? I have collision theory written down so that you remember and make sure you study what collision theory is, and that's on the board over there. Are there any questions about rates? Any questions I can go over about anything related to rates? These are the problems that you are going to be asked to do. They're just like this. If you can understand how these problems work forward and backwards, up and down, side to side, just in all the angles, these simple problems, that is how they're always asked. Even the luminol problem, which looked a little bit weird, was really just looking at the slope of 2 reactions and saying, hey, I got 2 different Ks at 2 temperatures, and I can solve for like an activation energy using the equations I have in my toolbox. Okay?
Those graphs right there, is that the activation energy one?
These are activation energy, and if you have time in the end, I'll go over that. Or I can talk to anybody about that. It was just a little side note I put up, but we can do that later. But we want to keep time for this.
Okay, so switching gears to chapter 21, radioactivity. Okay, the first thing I want to go through is all the types of radioactive decay that you're going to see, all right? Now, there's actually 5. I didn't write gamma up there because gamma doesn't really result in a new nuclide. It's basically just electromagnetic radiation. So just know that. It's electromagnetic. It doesn't necessarily result in the form of a new nuclide like these ones do. So these are the 4 ones that mainly you're going to use, okay? So what I would do is copy this down in your notes so you can see exactly what each of these types of decay does, okay? It's so important to know exactly what a beta decay particle is, what an alpha particle is. Because if you don't know what those are, you're going to be completely stumped on these type of problems, okay? So first, alpha decay. Yes?
Will neutron capture be on the test?
I'm sorry?
Will neutron capture be on the test too?
Yeah, look that one over as well. So neutron capture is basically, it's a lot to do with fission reactions. It's basically just shooting a neutron at something and making it unstable. So then it will start decaying. Typically, if you have something that's stable and you want it to decay, then you can shoot a neutron at it and make it unstable, and then it will decay. So that's basically what neutron capture is, and that's a lot what fission is. Okay, so one other thing to note with these radioactive problems is it's so important to pay attention to the verbiage that they use here. Okay, so for example, if I'm talking about alpha decay, I'm going to emit an alpha particle. If I'm talking about beta decay, I'm going to emit a beta particle. All right. However, if I say I have radon-222 and I bombard it with alpha particles, then that's not emitting alpha particles, it's sucking in alpha particles. So make sure that you know, read into it. If it's decaying, then it's emitting particles. If we're bombarding it or if it's shooting something at it, then it's going to accept an alpha particle, and that's going to completely change. So don't get so stuck in your head that in alpha decay, the alpha particle always has to be as a product, because we can shoot alpha particles at something as well. Okay? So going through this, we'll just write out what the product of each one of these types of decays would be using radon-222 as our example. So first, an alpha decay, we're going to emit an alpha particle, which is a helium nucleus, right? Now the whole idea with these radioactive decay problems is we just want to balance the two reactions, okay? So we're going to treat this arrow as an equal sign. We're just going to get the top numbers to equal across. We're going to get the bottom numbers to equal across. It's that simple. So I have 222 over here. I know I have to add up to 222 over here. So to get there, I'm going to need 218. I have 86 over here, and I already have 2 over here, so I'm going to get 84, and that's polonium. Okay? A beta decay. On your smart work, sometimes they would just write it as the symbol beta. You can do it that way, but I recommend actually using the way I'm going to write it, because it helps you keep track of the numbers better. Okay? Don't just write a beta unless you really have this stuff down. If you don't have it nailed down, I would use this symbol because you're going to be able to keep track of it better. Okay? So a beta particle is basically, we just notate it as an electron. 0, -1, E. Right? So now, the nuclei that's formed here, I have 86 over here, and I have a -1 over here. So my bottom number is going to have to be 1 higher than this originally was. Okay? So this is going to be 87, 222, 0, it stays 222, okay? And then we just look up what element that is, and it is francium, Fr. Okay? Next is positron emission. What a positron is, it's a positively charged electron, okay? And again, read into the wordage, emission, we're emitting a positron, okay? So this one is just a positively charged electron. So 0 + 1 E. And then we just want to get this to balance. I have 86 over here. I have 1 over here. That means I have 85 left. And the top number stays the same. And this is actin or something. I can't remember the name of it. It's not that important. Just know the symbol. Okay, now electron capture. Electron capture, again, the wordage, we're capturing an electron, all right? So I'm going to have a 0, -1, E. Now I want to get these two to balance. I have 86 -1, that's a total of 85. So on the right, I have to have 85. Top number didn't change, okay? So 222, and that's AT. Okay, any questions on that? Okay. So now what we're going to do is we're going to look into how we can predict what type of decay a certain isotope or nuclide will do. All right? And we do that using the belt of stability. What the belt of stability is, it's a graph of protons as your x-axis and neutrons as your y-axis. And on your belt of stability, there's a bunch of little dots. Okay? And each one of these dots represents a stable isotope. So the whole point of radioactive decay, the whole reason things decay is because they're unstable and they want to become stable. So in order to become stable, they will emit different particles and they will undergo these different types of decay to get to a stable nuclide. All right? So for example, if we were really doing this for radon-222, what I would want to do is go to my belt of stability and find out exactly where this lands on the chart, okay? Now I'm going to give you, this is in the slides, but I'm going to go over it again, of the general trends of what type of decay you're going to do depending on where you land on the belt of stability, okay? So if you're above the belt of stability, you're going to be doing beta decay to get down, all right? If you're above the belt of stability, like way up here, usually 84 protons or more, you're going to be doing alpha decay, and that goes in that direction. And then you notice here, positron emission and electron capture got us the same exact nuclide, right? They do the same exact thing. So those are both going to be on the bottom. The only difference is that if we have a light nuclei, meaning one that doesn't have a ton of protons in it, it's going to be more likely to do positron emission rather than electron capture. So we can just notate that like this. Is coming up, we're going to want to do positron emission. As soon as we get to nuclei that have more protons, it's going to be more likely to do electron capture. There's no definitive line that says, okay, at 56 protons it does electron capture and not positron emission. It's kind of just a general trend. So if he were to give you something that has like 3 protons and it was below the belt of stability, I would say, okay, let's do positron emission rather than electron capture. But essentially, they do the same exact thing. Okay? Yes?
Will we then be given this belt of stability on the test?
Yes. If you need it, it will be attached.
Excellent.
I haven't seen the exam, but I'm assuming you're going to need it, so I'm assuming it's going to be attached. Yep. Okay. So now, again, back to our example of radon-222. If I really want to figure out what type of decay that's going to do, I use my belt of stability. So what I would do is I would count off 86 protons. And on the belt of stability, you'll be able to see every single dot. So you will see a dot for every single proton. So you have to be really exact. So I would count off 86 protons, and then I would go up however many neutrons that is. What is it? 136? What is it? 136? Okay. So then I'd go up over 86 protons, up 136 neutrons, and then I'd see where that landed. If it landed above the belt, then it would want to do beta decay, for example. So we can predict what type of decay it's going to do. Yes?
Could you look at the periodic table and guesstimate based on the average atomic mass there?
You can. Like, especially for the heavier ones, anything over 84 protons is, like, it does alpha decay often. I'm not going to say it always does alpha decay, but that's typically what it does, is because it wants to get down. But the best and most thorough thing you can do is to count off on the chart and see where it is. Yes?
What does it mean if it falls like directly on the belt?
So, okay, that's a good point to bring up. If it falls, so on the belt of stability, you'll see like a shaded area. If it falls in the shaded area, it doesn't mean anything. It does not tell us anything. The only thing that we're looking for is if it falls on an exact dot on the belt of stability. If it falls on an exact dot on the belt of stability, then it's stable. If it just falls in the shaded region, it doesn't tell us anything. It still needs to get to a specific dot on the belt of stability. Yes?
So really we're looking for what's above or below that specific dot.
Say it again. Say it louder.
So really we're looking for what's above or below that specific dot.
Exactly. Exactly. Yep. And oftentimes there's going to be multiple things that it can do. So the type of problem that I see coming up on the exam is him telling you, okay, we have a sample of radon 222. Get that into lead in 5 steps or less. And you have to be able to use these equations and do whatever you have to do, whatever type of decay you want to do, but in 5 steps or less, turn radon 222 into lead. That's the type of thing I see being on the exam. So make sure you understand each of these and the nuclides that form. Yes?
So if you're changing that, for example, to lead, how can you change, what are the rules to change the coefficients of the beta particles and the alpha particles?
No, that you have to use them as they are. You have to use them as they are. That's just an example that I came up with, radon into lead, but it can be anything. It can be turning lead into gold, like he talked about in class. Yeah.
Would you have to make sure that that one's also not radioactive? Like, would you have to find it on the belt of stability and make sure that the neutrons and everything match up?
I think for the problem, he's just going to tell you, I want this into this. That's how I've seen it in the past, but he could have you start with radon 222 and get it to a stable nuclide. And then you just have to use the belt of stability and figure out once you hit a stable one for the dot. Okay, we got to move on. By the way, we're going to go till 9 o'clock. We're not going to stop at the 50, just so we have a lot of material to go over. And it's kind of hard when people start getting up and stuff. Okay, next thing I want to go over is half-life reactions, okay? There's an equation that's not on your equation sheet that you need to know for half-lives, okay? I'm going to write it down. It's AT over A initial equals 0.5 raised to the time over time 1/2. Okay? You need to know this equation. It's not on your equation sheet, but it's going to make your half-life calculations so much easier. Let's go over briefly, yes. Yes, you can do the same thing. There's 2 ways you can do it. I'm going to show it to you this way, but you can also use the integrated rate law for the first order and then use the half-life. Either one works. I'm going to show it to you this way, though, because it kind of does all of it in one step instead of you having to use 2 equations. Okay, so reading this. How long will it take for a 40-gram sample of iodine 231, which has a half-life of about 8 days, to decrease by 99% of its original mass? Okay? Now let's go through what each of these things are in this equation. AT is a concentration or an amount or anything after this amount of time that we're referring to. Okay? So, in this problem, I'm talking about, this is what I want to solve for in this problem. Okay? So I'm trying to solve for this T in this problem. But AT is always what's left after the time that we're talking about. Okay? And AO is the initial amount that we had. Whether it's a gram amount, concentration, doesn't matter. It can be like a decay rate. It's just whatever was at the beginning, and this is whatever was at the end of that time. Okay? And then this is pretty self-explanatory. Time is the time that we're referring to, and the T1/2 is the half-life time. Okay? So using this equation, we can solve this problem. Just plug everything in. Okay? So the first thing, what is AT over AO? Okay, this is something I wanted to trick you guys on. This is not 0.99. Again, it's so important to read into the words that they use. This decreases by 99%. If it decreases by 99%, then I have 1% left. Okay? If it decreases to 1%, then I have 1%. Oh, so if it decreases to 99% of its original, then this ratio is 0.99. Okay? So watch out for the words that they use. So this ratio right here is going to be 0.01, 1%, right? So I'm just going to start plugging stuff in. 0.01 is going to equal 0.5 raised to the T That's what I'm solving for, is how long it's going to take, and the half-life time is 8.04 days. So I can plug that straight in as 8.04, but just know that if I plug this in as 8.04 using days as my unit, then this time is also going to come out in days. So look at your answers. If they want it in seconds or if they want it in years, you're going to end up having to do dimensional after that. Okay? And this has the same type of log rules that Braden was talking about. All right? So if we have an unknown variable in an exponent, we can bring it down into the front and take the log of both sides. So I'm basically moving this down right here and then taking the log. So t over 8.04 times the log of 0.5 equals the log of 0.01. And then we'd end up dividing by the log of 0.5, and then we'd end up multiplying by 8.04 to isolate t. And for the sake of when you're watching this video again, you should get 53.4 days. Okay? Let's do another one. At time 0, there are 10 grams of tungsten 187. One thing to point out too, there's multiple ways they can write these nuclides. One of them's like this. They might just say tungsten 187. This 187 is referring to the mass number, so protons and neutrons combined. And if they don't necessarily tell you what that atom weighs, it's just 187 AMUs. So if they don't say like this is 187.013 AMUs, then we just say, okay, it's 187 AMUs. All right? So if the half-life is 21.6 hours, how much will be present after 2 days? Okay? So I'm going to use the same exact equation and start plugging stuff in. Notice that I want to find out how much is left after a certain amount of time. So AT is going to be what I'm solving for. So AT is my unknown. My initial amount is 10 grams. And that equals 0.5. And then I have T over T1 half. But notice here, one is in hours and one is in days. So make sure that when you plug these in, they're both in the same unit. So this is a pretty easy conversion. 2 days is 48 hours. So I'm just going to plug it in as that. It's going to be 21.6 over 48. Oh, did I do it wrong? Sorry. Thank you. Yes. So the time that we're going over the half-life time. Now when you do that, you can get this into a number. Just take 0.5 raised to that fraction, and then you're going to end up multiplying that by 10, and that gives you AT. And when you do that, you should get 2.14 grams. So these half-life problems, they're really actually not that hard, as long as you know how to use this equation. If there's only so many ways they can ask one of these problems. They can only ask you for an original amount, an ending amount, the time that it went, or the half-life time. They will always give you everything except one variable. Yes?
I was going to ask if maybe they give us one less variable than we need. And they ask us to find it using like one or two other equations.
Yeah, they could do that. Yeah, for something like that, it'd probably be a free response. But for a multiple choice, it'd probably just be one step.
Would you say we just need to know that like our half-life equation from the toolbox or
Definitely.
any other equation?
Definitely. Yep. Know everything on the toolbox. Okay. Moving on. Okay. So the next thing that we're going to go over is nuclear binding energy. Okay, we'll do this one first and then we'll do nuclear binding energy, just to make sure we have time for this one. This is the type of problem that Dr. Macedoni just went over in his very last lecture at the very end. It was a black slide with yellow print and it had a bunch of conversions. This is the same exact type of problem, okay? So, what we're looking at here is we want to know how many nuclei are present in a sample of 230 thorium. which has a half-life of 24.1 days, and it has an activity of 2.1 millicuries. Okay? What an activity means is its disintegrations. All right? The activity is how much is disintegrating. Now, when you read this problem, I know you guys haven't had a ton of practice with this, but there's an equation that you need to know that you should immediately think of as soon as they talk about how many nuclei are present, okay? And that equation is rate equals Kn. Make sure you know that one. It's the only way you can solve this. Yes. In terms of A, I'm not sure what you mean. Okay, so the first thing we need to do is understand what units these things have to be in order to do this, okay? Most importantly, rate has to be in disintegrations per second. It has to be in disintegrations per second. Millicurie is not disintegrations per second. Neither is Curie. But there's a conversion on your equation sheet that lets you get from Curie to millicurie, or Curie to disintegrations per second, okay? So the first thing I want to do is get this rate into disintegrations per second. So I have 2.12 millicurie. There's 1,000 millicurie in 1 curie. And in 1 curie, there's 3.7 times 10 to the 10 disintegrations per second. Notice here the units cancel, and I'm left in disintegrations per second. Now when you do that, you should get 7.844 times 10 to the 7th, and the unit there is disintegrations per second. Okay? So now I have my rate, where I can plug this in for the rate. Again, they want to know how many nuclei. So N is the thing that I'm trying to solve for. But I got to find K. All right? So how can we find K? The half-life equation. Good. Another thing to note is that, is this sample radioactive? Is TH radioactive? Yes, right? Because it has more than 84 protons. 84 protons or more, then that thing's radioactive. And radioactivity is always first order. Okay? That's something to note. Radioactivity is always first order. So if I want to solve for a K, I can use those first order reactions to do it. All right? And the one that you pointed out was the half-life one. So T1 half equals 0.693 over K. But the problem here is that 0.693 in this K, this is all based on second units. As in, we have to have everything in seconds. So the half-life that you were given is 24.1 days. So we have to convert that to seconds. Okay? Now, for the sake of time, I'm not going to do the dimensional analysis. I'll just tell you what it is. It's 2.082 times 10 to the 6th seconds. Okay? So now that we have our half-life in here as seconds, we can just easily solve for K. All right? And then when you do that, you get K equals 3.329 times 10 to the negative 7. So notice now, I've got my K and I've got my rate in disintegrations per second. So now all I do is plug them straight into this equation. So 7.844 times 10 to the 7th is going to equal, my K is 3.329 times 10 to the negative 7th times N. And when you do that, N will equal, sorry, this is getting a little low, 2.356 times 10 to the 14. And that is nuclei. Yes?
Where did the 0.693 come from?
That is from the first order half-life reaction. Yes? Units on K. it would be, what would it be? Inverse seconds, hertz, because it's first order. Okay, so we've got a few more minutes. I think we can get to this very last problem. If we're not able to calculate it all out, the least I want to do is talk conceptually about mass defect, okay? So what mass defect is, it's the energy that is holding the nucleus together, okay? So when we talk about nuclear binding energy, we're going to use Einstein's equation. E equals mc squared. M is the mass defect, and it's always in kilograms, okay? So essentially what we're saying here is that there is an energy associated with holding the nucleus together, and because I have that energy there, some mass is actually lost. So if I want to find the nuclear binding energy of a carbon-14 atom, there's a simple formula that you use, okay? So I want you to write this down. It's the sum of the individual nucleons minus the mass of the nucleus. That is going to equal your mass defect. Okay? So again, in more simple terms, what I'm essentially figuring out here is in carbon-14, I have 6 protons and 8 electrons. So if I had a bucket of 8 neutrons. If I had a bucket of 6 protons and 8 neutrons, what's the mass of that? Okay? I calculate that, and then I go to subtract that from the mass of the actual nucleus. Now, what Einstein figured out is that when these 6 protons and 8 neutrons actually get globbed together in a nucleus, the mass of the nucleus is actually less. And that's because some of that mass was converted into the binding energy, which holds the whole nucleus together. Okay? So if you follow this formula, you'll always get it. Now, one thing to note here, in this problem, they gave me the mass of an atom in AMUs, right? What's the problem with that? It's not in kilograms, and more importantly, what is included in this mass of the atom? Protons, neutrons, and electrons. So I'm only comparing here the mass of these nucleons, subtracting the mass of the nucleus. So what I have to do is I have to convert this AMUs into kilograms, which you can do from your equation sheet. Once you have it in kilograms, you have to subtract out the mass of the electrons, okay? You always have to subtract out the mass of the electrons, so we're only comparing nucleons to nucleons. If you just plug in this mass, you will get it wrong, okay? You have to subtract out the electrons, yes?
Will we be given the mass of protons, neutrons, and electrons? We have to know.
They're on your equation sheet. So on the left-hand column, kind of towards the top, you'll see m sub e, m sub n. That's the mass of an electron, mass of a neutron, and they're given to you in kilograms there. Yes?
So you do the mass of the electron times 6,
Exactly.
and then subtract that out.
Exactly. So whatever the mass is, multiply it by 6. It's the sum of all these masses.